Since the beginning of this unit, we've learned 3 different hand rules. The first hand rule, called the wire grasp rule, is simply used to find the direction of the magnetic field that's caused by a moving charge. It's only been a week since we've done that, okay, but it seems like forever ago now. Okay, its purpose is to find the direction of the magnetic field caused by a moving charge. That's it. That's it. There's no external magnetic field. There's no magnets in here. We're not paying any attention to the Earth's magnetic field. You've got a wire with current going through it, or you simply got even just moving charged particles moving through the air. They generate a magnetic field. What's that magnetic field look like? Done. That's what the wire grasp rule is for. The second rule that we called the coil rule for solenoids, and this is what we had our quiz on today. It's a little bit trickier, but it's still used in almost the same situation. Okay, the coil rule for solenoids is used when we want to find the polarity of a coil of wire that has an electric current going through it, the polarity of a solenoid. Okay, but in essence, that's still moving charged particles generating a magnetic field. It's still essentially the same thing, but a specific case of the same thing. We can actually use the wire grasp rule to find the polarity of that solenoid, but I think it's easier to use the coil rule for solenoids, so that's what we're going to do. We're going to use it whenever we want to find the polarity of a solenoid, or if we have the polarity of the solenoid and we want to work backwards. The hand rule that we learned yesterday was the hand rule for deflection. This one is different. Okay, I wouldn't suggest that it's harder necessarily. Some people find it easier because you don't need to wrap your hands around anything and see which way your fingertips point and so on and so on. But there is a little bit more to it. The hand rule for deflection is used to find the direction not of a field, but rather of a force, a magnetic force. There is no force in the first two because all you got is the wire and the magnetic field caused by that wire. There's a force in the last case because you've got the wire or the moving charge producing a magnetic field, but you've also got an external magnetic field. Maybe it's magnets, maybe it's the Earth's magnetic field, maybe it's some other electromagnet. It doesn't matter what it's caused by, but there's an external magnetic field. So you've got moving charge in an external, and that's important, right? External. If you could read it, it would be even more important. And typically we want to find the direction of the magnetic force there. Okay? Again, if you're dealing with a force, it's got to be the third rule. Now, how do we do each of these rules? Each of them have different variables. The first two have the same variables. There's the thumb and the fingers. The third one has the thumb, the fingers, and the palm. The thumb, for the first one, points in the direction of the moving charge. If the electron is moving towards the right side of the room, then you stick your right thumb towards the right side of the room. If an alpha particle is moving towards the right side of the room, you'd stick your, what did I say? I think I said for the electron it would be the right. Yeah, for the electron it would be your left thumb towards the right side of the room. Okay, if it's an alpha particle, you would stick your right thumb in the direction of that particle towards the right side of the room or whatever it was. Your fingers in the wire grasp rule are going to be bent a little bit, a lot, it doesn't really matter. Your bent fingers are going to point in the direction of the magnetic field caused by the moving charge. There is no external magnetic field, right? There is no other magnetic field. Look, you got two things. You got a current and you got a magnetic field. One thing's got to point in one of those directions, one thing's got to point in the other. For the coil rule for solenoids, it's exactly the opposite, even though ultimately we're essentially trying to find the same thing. We've got a direction of the current typically, and we want to find the direction of the field. But this time our fingers, our bent fingers, or our clenched fingers, are going to point in the direction of the moving charge, which is the electric current. And our thumb is going to point in the direction of the magnetic field caused by the solenoid. But remember, it's the magnetic field inside the coil, inside the solenoid. So in other words, it's not pointing from north to south like we usually see. Rather, it's pointing from south to north. The hand rule for deflection, this is when we've got the charged particle, let's say, going into the page, producing its own magnetic field that would be, in this case, counterclockwise. But at the same time, it's exposed to some other external magnetic field here. You get two magnetic fields. Those two magnetic fields interact in kind of an odd way. They produce a magnetic force that's perpendicular to both of those things. So here's how we do it. We stick our thumb in the direction of the moving charge, just like we did for the first rule. Our fingers, which this time aren't bent, but this time are straight, they're going to point in the direction of the external magnetic field, not the magnetic field that's caused by the moving charge. There is one, right? There's a circular magnetic field caused by the moving charge. But my fingers aren't going in that direction. My fingers are going to the right side of this page in the direction of the external magnetic field. And my palm will just be there. Okay, my palm will be automatically pointing in the direction of the magnetic force. So if you got a charged particle, let's say going towards the back of the room, and a magnetic field pointing towards the left side of the room, thumb, fingers, palm's going to point upwards towards the ceiling. Okay, whatever way your palm happens to point, that's the direction of the magnetic force. All right, that's how we get the direction of the magnetic force. It's kind of backwards the way we're doing this, right? Because usually when we do something involving a vector, we're getting the magnitude first, and then we worry about the direction. Here we get the direction, then we got to worry about the magnitude. So how is it that we get the magnitude of this force? Well, there's a pretty simple equation that we learned yesterday. It allows us to find the magnitude of that force. F is equal to QVB. B is the magnetic field strength in Tesla. V is the speed in meters per second. And of course, Q is the charge in coulombs. We usually see a little upside down T there between the V and the B. What does that tell us? What does that represent for us? Yeah, they got to be perpendicular. If you're going to use the hand rule and or this equation, the charge must be moving perpendicular to the direction of the magnetic field. So if you got a magnetic field going this way, to the right. By the way, if I put a positive particle in that magnetic field, which way does it go? To the right or left? To the right? How come? Because positive particles move in the direction of the field? Wrong. If it's an electric field, positive particles move in the direction of the field, right? If it's an electric field, positives move with the field, negatives move against the field. If it's a magnetic field, this positive particle sitting there in that magnetic field would do nothing. It doesn't experience a force. But if it's moving perpendicular to the field, then it experiences a force. So we're allowed to use the hand rule for deflection in this rule, or in this equation right here, to find the force if the particle is moving this way, or if the particle is moving this way, or if the particle is moving this way, or if the particle is moving this way. Because in all four of those cases, it's moving perpendicular to the field. But if the particle is moving this way, can't use the equation. Can't use the hand rule. If the particle is moving this way, we can't use the equation. We can't use the hand rule. Good news is, if it's moving this way or this way, we don't have to use the hand rule or the equation because the value of the force is 0. There is no force. Now, what happens if we have a charged particle moving this way? Not 90 degrees to the field, and it's not parallel to the field. Yep. It's not a physics 30 question, right? That's a first-year university question, which if you go on and take a physics course, you're not going to find it hard. Okay? It's not that hard at all. It's not really much harder than what we're doing right now, just that we don't have to do it, so we won't. All right. We had one question for homework last night, and it was on page 599, question number 1. Any issues with that question? That's a pretty straightforward question, right? We're only looking for the magnitude of it, right? Yep. Answer was 2.35 times 10 to the minus 18. It's using that equation, that's it, right? How do we know that equation's valid? Well, it tells us the particle is traveling perpendicularly through the magnetic field, we know the equation is always valid if it's moving perpendicular through the magnetic field, right? Let's try another one here. One that's a little bit harder than what you've just done. This one says a carbon ion, first time we've dealt with a carbon ion, has a mass of 2.01 times 10 to the minus 26 and a positive charge of 1.6 times 10 to the minus 19 coulombs. They give us the data for this, but you know what? They could give us a notation instead. If they say carbon plus, then that means 1 times the elementary charge, or 1.6 times 10 to the minus 19. If they gave us, say, oxygen 2 minus, then it would be negative 2 times the elementary charge. So they don't use that notation here, but be prepared for that down the road because you could see that. We got the charge. We've got a magnetic field here. They're perpendicular because the magnetic field is going from, which way is it, left to right, right to left? Forget about the magnetic field caused by the carbon ion, but the magnetic field caused by the magnets. Tyler, does it go from south to north or north to south? No. Other way. It goes from north to south. Outside of the magnets, north to south. Inside, south to north. Now, this carbon ion also generates its own magnetic field with positive particle. The magnetic field going into the page would be clockwise if we use the wired grasp rule. But in the end, that's not what we're trying to find. We're trying to find the direction of the force, and we're oh, wait. No, we're not, are we? What's happening here? We're saying it's going through in a straight line. Wait, how's it going to go through in a straight line? Isn't there a magnetic force on this? Hands up. Is there a magnetic force? Yes. Who says yes? Who says no? Okay, most people said yes. Yes, there is a magnetic force. So isn't that going to deflect it? It's going to deflect it unless something counters the magnetic force, right? What do you think might balance the magnetic force here? Gravity. Right, that's exactly right. We've got, if we look at this, thumb in the direction of the particle, fingers from north to south, the magnetic force is going to point upwards on it. If the magnetic force is upwards and the gravitational force is downwards, and those two forces are equal, then it's going to go in a straight line. The forces will balance and go in a straight line through there. So we're going to set them equal to each other, right? We just established that they are equal to each other. Let's set them equal to each other. QVB is equal to M times G. We're looking for V here. What do we got here? 2.01 times 10 to the minus 26 times 9.81 divided by 1.6 times 10 to the minus 19 times 6.32 times 10 to the minus 5. That's a pretty weak magnetic field, right? We said the magnetic field caused by bar magnets is usually in the range of 10 to the minus 2. Here it's about 1,000 times weaker. This is comparable to the magnetic field caused by the Earth. Do the math there, and I think it worked out to be something like 2 times 10 to the minus 2 or something like that. Bryce, you got 1.95 times 10 to the minus 2 meters per second. That's a pretty slow speed. Usually the speed of charged particles that we get from questions is quite a bit bigger than that. Okay, but this isn't impossible. It's just unusual, that's all. So we didn't have to do a hand rule there because we knew those two forces had to balance. But as a nice little check, we were able to see that the magnetic force was up due to the hand rule for deflection. And of course, the gravitational force would have been downward on it. Okay, let's have a look at questions on page 600 up to 2A. Do not do 2B, please. Take a look at number 1. Here it says, an electron with a charge of 1.6 times 10 to the minus 18 and a mass of 9.11. We know these values, right? Or at least they're on our data sheet, so they didn't really need to tell us. Okay, but they do. It makes it a little bit easier. We don't need to look on our data sheet. It's traveling west along the surface of the Earth at the equator. The magnitude of the magnetic field at this location is 5 times 10 to the minus 5. What's the minimum speed that the electron has to maintain in order to remain at the same height? This is a big deal for me, to remain at the same height. The last question that we did, that practice or the example question that we did, said we wanted to find the speed at which the deflecting force would balance the gravitational force. That's exactly what they're saying in this question too. They're just saying it in a different way. There's a magnetic force upwards, there's a gravitational force downwards, and those two forces have to balance if we're going to keep the same height above the Earth's surface, right? That's west, right? That's west, towards the mountains. I've got an electron, so I've got a thumb, my thumb traveling west, or my thumb pointing west. My fingers will point in the direction of the magnetic field, which is towards magnetic south, right, towards the Arctic. Okay, my palm points upward. The magnetic force is upward. The gravity force is downward. Balance to remain at the same height there. Something times 10 to the minus 6. Is that okay? Have a look at this question, guys. Page 72. I think it's on page 47 or 48 of your worksheet book. I'll give you a minute to do that, and then we'll take a look at it as a group. The question says, look, we got an electron moving to the right in 3 different fields. There's an electric field, a gravitational field, and a magnetic field. In each case, we want the force to be downward on this electron. We want it to be pushed. What kind of field would push an electron downwards if the field is pointing upwards? What kind of field would push an electron downwards if the field is pointing into the page? What kind of field would push an electron downwards if the field is pointing downwards? Okay, let's go with gravity first, because that's the easiest one. If you've got a charged particle with mass, which of course all charged particles have is mass, and that charged particle is, we want it to experience a force downward, then there's got to be a downward field. Okay, downward gravity causes a downward force. That means that the third field, has got to be gravity. Okay, that's the easiest one. The next easiest one is electricity, the electric field. The electric field, if we want a negatively charged particle to be pushed downward, then that electric field has to be acting upwards. Because remember, with the electric fields, the charge moves opposite to the field if it's a negative charge. That means this is the electric field. Now, like we said on the quiz, okay, we have an answer now, right? We know what the answer is. The last one's got to be magnetic. Okay, if you're rushed for time, then pencil in an answer right now. If you've got time, then let's just double check the final one to make sure that we haven't made a mistake with one of the other ones, okay? Let's assume that it's a magnetic field. We got our thumb going to the right, fingers going into the page. The force would be downward. Sure enough, it agrees with the hand rule, therefore that's got to be the magnetic field. The answer is therefore going to be A, electric, magnetic, and gravitational field. All right? Let's spend a couple minutes, in just a couple minutes, going over a little bit more detailed analysis of this charged particle in a magnetic field. Let's draw a picture of the magnetic field again. The magnetic field in this case is going to be pointing into the page. We could draw it out of the page just as easily. It doesn't matter. We got a negatively charged particle. We could make it positively charged particle. It doesn't really matter. We got a negatively charged particle going to the right in that magnetic field. We know that that negatively charged particle experiences a force. We learned this yesterday, right? We can calculate the magnitude of that force by QVB since it's moving perpendicular to the field. Okay, fair game. The equation is fair game. But so is the hand rule for deflection fair game because it's moving perpendicular to the field. Let's find the direction of the force on this particle now. Thumb in the direction of the particle, fingers in the direction of the field, thumb to the right, fingers into the page, palm points downward, right? So we're going to say the magnetic force is downwards. And green is going to be the velocity, so the direction of motion. All right. If this particle is moving to the right but experiences a force downwards, where does it go? Does it keep going to the right? Does it keep going to the right? Okay, good, good. It keeps going to the right, but not straight to the right. It goes down a bit as well. You kind of jumped ahead of my next question. Which was going to be, if it doesn't go to the right, straight to the right, is it going to go downwards? Well, kind of. It doesn't go straight downwards, right? It's moving to the right. It's got a magnetic force downwards. It's going to go somewhere in between, right? Somewhere in between the way it was moving and the way the force acts. So it's going to go like, I don't know, something like this. Thumb in the direction of the particle, which is kind of diagonal down and to the right. Fingers field into the page. Palm points to the left and down, like this. Where's the particle going to go next? Thumb in the direction of the particle. Fingers field. Palm points to the left. Goes somewhere in between. Thumb in the direction of the particle. This is when it really gets hard with that rotator cuff thing. Thumb in the direction of the particle. Fingers field. Palm points up and to the left. We could keep drawing. We could draw that in. What do you notice, first of all, about the force, the red force? Do you notice a pattern? And if so, that's kind of a loaded question, right? Do you notice a pattern? And if so, what's the pattern? Well, clearly there must be a pattern, right? Otherwise, there wouldn't have been an if so. What's the pattern here? What do you notice about that red magnetic force? In each case, what's the same about the magnetic force in each one of these four cases? Okay, Michael, you're right. It's 90 degrees to the direction of motion of the particle. Okay, and that makes sense, right? Because we know that it's always got to be 90 degrees. If the particle is moving one way, the field is 90 degrees to the way the particle is moving, then the force is going to be 90 degrees to both of those. Good. So it's going to be 90 degrees. What else? Yep. They all point to the same spot. Okay, that's the one I was looking for. Okay, all the forces point to the same spot. That spot right there. That spot that seems to be in the middle, is kind of in the middle, in the center of the, what's the shape of that path? Yeah, it does, doesn't it? It looks like it's going to become circular. So the force, the magnetic force, which we can describe by the equation that we learned yesterday, QVB, the magnetic force always points toward the center of a circle. What's another name for a force that points toward the center of a circle? The centripetal force. Good. From physics 20, right? If that magnetic force points toward the center of a circle, we could call it the magnetic force, or we could call it the centripetal force. If we call it the centripetal force, we could describe it by this equation that you learned in physics 20. You guys also learned in physics 20 that the centripetal force is not a fundamental force. It's always caused by something else. Like, for instance, in the case of a car going around a turn, it's caused by friction. In the case of the Earth going around the sun, it's caused by gravity. In the case of the electron going around the nucleus, it's caused by an electric force. In the case of an electron going in this magnetic field, it's caused by a magnetic force. If the magnetic force causes the centripetal force, then there's no reason why we can't set those two equal to each other. Fc equals Fm. So now we've got the equation that we learned yesterday. We're not throwing that out. That's still perfectly valid. Everything that you've done so far is still perfectly valid. It's just that now we have a few more tools in the toolbox. Okay? What you learned yesterday was like trying to build a house with a hammer. Okay, that's an important tool when you're trying to build a house. But now we have a saw, and now we have a level. Now we have more tools in the toolbox. The hammer is still valid, and it's still really important. But now we've got some other important tools that will help us to do some other things. Okay, does that make sense? When a charged particle moves in a magnetic field, its path will always be circular. Now, you can see here that this charged particle looks like it leaves the magnetic field, and when it leaves the magnetic field, it's going to go off in a straight line. It didn't follow a complete circle, but while it was in the magnetic field, it was a circular path. If it was going quite a bit faster, then that charged particle might have went like this, and then skipped out the other side in a straight line. That's only like 1/8 of a circle. But while it was in the magnetic field, it was still following a circular path. So, regardless of whether it goes in a complete circle or a partial circle like we have here, all three of these equations, including the two new ones we learned today, are all valid. Make sense? We don't have time to do a problem with this today. We'll pick up where we left off tomorrow. But I want to leave you with one little thing here. Okay. All three of these equations are valid. Just like back in physics 20, we needed acceleration equations. All of those equations, A equals delta V over delta T, D is equal to VIT plus 1/2 AT squared, etc. All those were valid. We just picked the ones that fit the givens the best. That's what you do here. You got a charged particle in a magnetic field. All three of them are valid. Pick the one that fits the givens the best. Generally, if you've got the word radius mentioned, usually 90% of the time if you have the word radius mentioned, you're going to do this. Got it? That's what I'd try first. If it doesn't work for me, well then try something else because you got a couple more valid things. But if it mentions the word radius, you're likely going to use this one. All right.